So for probability regression then, the basic aim remains regressing or explaining probabilities. It's just a slightly different way of doing this than for logic regression. The basic problem is still, how do you squash probabilities lie between 0 and 1? So for probability regression model, how this is done is that z minus 1 of the probability equals to the regression bit, and z to the minus 1 is the inverse CDF of a normal distribution. So what this means is that you apply the function z to the regression bit. This then gives you the probability value. Now, if you were doing a hand calculation, and this was something you'd be asked to do on a final written exam, then this would be z of the regression bit, where z is a normal distribution value from tables. Now, it turns out that if you're asked to do a computation as part of the coursework assignment for this module, then in R, the function z is something called p-norm. So I'll go through that more carefully later on in the lecture, but this is how you sort of write this down mathematically. The probability would be z of the regression bit, but in R, the computation that you would need, you would require the function p-norm. Okay, basic problem again, just a slightly different way of squashing down to lie between 1 from this regression model. So for the R code for linear models and generalized linear models, I just wanted to clarify that this derives from some of the background underlying maths. You don't have to know the underlying maths, it's just if you're aware that there is a backstory, it actually makes it easier to program in R and understand what you've got to do. Okay, so technically speaking, logistic and probit regressions are examples of something called generalized linear models. Now this is a technical maths term, it just means essentially a posh way of saying hard regression model. As part of that, because these are hard regression models, the R command you use is GLM for generalized linear model, so it reflects this technical maths term, and it just means literally a harder regression model than the base case. So in contrast, regression models are known as a linear model, which is why the basic R command for regression is LM for linear model. Okay, so the maths is slightly harder, and so you have a slightly different R command to reflect that. So for standard regression, the linear model, the R command is LM. For harder regression, the posh maths term for that is generalized linear model, and the R code used that reflects that is GLM, which just stands for generalized linear model. Okay, don't expect to know some of the maths behind this, but if you know that there's a backstory, it makes certain things easier. So in addition to the fact that you need the R command GLM for generalized linear model, in R you also have to specify that family distributions used is binomial. So this just essentially tells R that you are regressing probabilities. So remember, R is just R for robot. You've got to tell it exactly what to do, nothing more, nothing less. Beyond telling R that you are regressing probabilities, you also have to tell R what link function you are using. Now the default is sensibly chosen and is the logit regression model. This is thought to be the slightly better probability model mathematically, although both the logit and probit model should give you similar answers. And if you don't specify which link function to use, it will fit a logistic regression model as the default. If instead you want to fit a probit model, then you'd have to tell R that you specifically wanted to fit a probit model. Okay, so all these things are essentially bits of R syntax, so it's just a little bit like learning a slightly different version of Microsoft Excel. Okay, but it is important to be aware that these do fundamentally have a mathematical and statistical origin and underpinning. Now you don't need to know the backstory, but awareness that there is a backstory actually makes a whole host of things easier in terms of the R programming and the R syntax. Now one thing that can be slightly confusing here is the required data structure for probability models in R. So to fit a binomial generalized linear model in R, you just need to have the data organized in terms of columns of successes and failures. And probably the best way to remember this is if you think you're fitting a probability regression model in R, just thinking in terms of successes and failures. What you have to do is to bind these columns of successes and failures together, and the R command needed to do this is cbind. So it just literally again means bind the columns together. The R function for that is cbind. So for the example in R, so you would define the number of tested components as follows. So standard way of doing it, tested goes to the concatenation of a list of data in the brackets, each data point separated by a comma and a space. So that's the same for tested and failures. And then the successes is just the difference between the tested minus the failures. So each item that's tested, it either succeeds or it fails. And if it doesn't fail, it must necessarily be a success. And so the difference between these two, tested minus failures, is the successes. And then the crucial thing you have to do is bind the successes and failures together using the command cbind. That fasteners, and fasteners will be the live variable in the R syntax when you're fitting the logit and probit model. So what you should see here is that much of the statistics and statistical interpretation of these probability regression models follows from the standard linear regression model, and alongside that, much of the way that the R code is organized also follows for the situation you have with the standard regression models. Okay, so this is an early example of, if you're aware of the sort of mathematical and statistical backstory, it actually makes R easier to learn and to pick up. So you have this generic two-step process then. So first of all, compute the model, and then in the second step, summarize the results. So here we have then the either A.glm or B.glm. So it's a generalized linear model. You're trying to relate the fasteners variable on the previous slide to the load. The family is the binomial. So this is telling R that you're fitting a probability regression model, and then for the probit you actually have to specify that the link equals probit. It will fit a logistic regression model as the default. I also want to say here, I think there is a subtlety, and this is something that I wouldn't always have had the experience and the maturity to fully appreciate. So these models should serve as a cross-check of each other in applications like dissertation projects. Look for similar models giving you similar interpretations and numerically similar. So we're back to this work numerical example then. So these aircraft fasteners, and I just wanted to sort of show you how you would answer these three basic problems then. So you're asked to fit linear probability, logistic and probit models to this data and interpret the results. So again, you would expect to find very similar interpretation in each case. So what we're going to expect to find is that as the load increases, the probability of failure will increase. Equivalently, as the load increases, the probability of success will decrease, and that should be true for all three different models. The different models, though, will have perhaps markedly different ways in terms of how you quantify the relationship between the load that's applied and the probability of success. So you're asked there to find the value of the load that would cause 50% of the components to fail. Now in the middle of the sample you'd expect these three models to give you roughly similar answers, but then at either end of the scale you might get marked differences. So if you've got a low load applied, you might have probabilities that are estimated to be close to 0, and if you have a high load applied, it might be incredibly likely that these components will fail, so you might get probability estimates that are closer to 1. And the logit and probit model should give you sensible estimates. The linear probability model might give you estimates outside the 0-1 range. So for the linear probability model in R, the thing that you want to focus on for this bit with the computations is the linear bit. So we're just going to treat this as a straightforward linear regression on the probability of success. So if you look back a few slides, we showed you how you calculate the probability of success, and all you now do is just fit a linear model of this success probability against the load. So call it something here, A.lm, and remember it's the same syntax that we've seen before, the linear model of the probability of success related to the load, and then the second command to summarize the results. So this is something you've seen now in the other lectures. There's this two-step process for how this thing works in R. first of all, run some computations and call it something logical. Secondly, call that up with the summary command, which will display you the results. Okay, so this is like a robot. R is like a robot. It will do exactly what you tell it to do, nothing more, nothing less. So it will do the precise computation in the first step, then the summary command would be needed to show you the results. Okay, and then all we've got in this case is a linear regression model for the y variable being the probability of success. So in this case, the linear probability model is easier to set up than the binomial generalized linear models, the lead logit and the probit. So with these binomial generalized linear models in R then, so the key difference here is that you need the columns of successes and failures bound together with the command cbind, and this is what this variable here, fasteners, is. This is the columns of success and failures bound together. Much of the rest of the R syntax and interpretation follows from before. So you have the first set of commands, which is a computational command, and then the second summary command to display the results. And how the syntax works would be, this is a generalized linear model. The fastener is related to the load. Family equals binomial. That bit tells you, well, tells R that you are fitting a probability regression model, not just a standard regression model. And then the extra bit to specify if you want to fit a probit model rather than a logit model. Okay, so much of this should be similar to the linear regression model fitted on the previous slide. Okay, and this always works in the same way, essentially. One step of commands to do the computation, another set of commands to summarize the results. Okay, and much the same thing works as before. It's just now we've got a harder probability regression model, not just a classical linear regression model. So in terms of the interpretation of results then, all statistical software packages produce redundant information. That's true for R and E views. And really the name of the game isn't just producing a lot of computer output. The name of the game is the value added provided by your analysis, just picking out the bits of the output that you need. Now the natural thing to focus on in terms of the assessment for this module, which will be an individual coursework, I would expect you to calculate a t-statistic. So this is a slightly different way to how you've seen this phrase before, because we're now interested in the probability increasing or decreasing, not the y variable itself. But again, much of the way this is set out is familiar, hopefully, from the classical regression models we looked at before. So if you calculate the t-statistic, the first thing to ask is the variable in question significant? If it is significant, if the variable increases, does the probability of a success either increase or decrease? And this depends on if the variable is significant, if the estimate is either positive or negative. Okay, so it's liable to be a lot easier than it might seem at first. So technically speaking, these are probabilities that are increasing or decreasing, but the interpretation and much of the mechanics of the regression type output works in exactly the same way as you've seen before for the classical linear regression models. The first thing I want to go through then is this linear probability model. So we've got the t-statistics here, and the thing to look for here, the interesting bit would be the second row of this table downwards. So ignore the intercept coefficient of load. So this is significant, as you can see that the final in the column is 6 times 10 to the minus 10, which is much less than 0.05. It's equivalently accompanied by 6's here. Interpret this as load has a significant impact on the probability of success, precisely because the 0.05 estimated coefficient is negative, so as load increases, the probability of success increases. And then in this example, because it's a linear probability model, if you increase the load by 1 kilogram, you increase the success probability by 6 times 10 to the minus 4. Now, given an example of a calculation of a statistic or t-statistic similar to what you might see on an exam type question, don't worry about this year. The main thing would be this year just being able to compute this in R. Then quantities. So verify here, if you do this hand calculation, actually what you've got is the inequality signs a different way as your cross-check that you haven't made a mistake of interpreting the p-values.